All right, so in this lecture, I'm going to go over homework problems from Chapter 4 on vector spaces and linear transformations. So the first set was in section 4.2 on page 10. So let me do some of those problems. We start with certain vectors in R2. V1 is the vector 1, 1. V2 is the vector 3, 5. V3 is the vector 11, 4. And we want to find scalars, not all zero. We want to find scalars x1, x2, x3, not all zero, such that if we take the linear combination x1, v1 plus x2, v2 plus x3, v3, we get the zero vector. Again, remember, this is the zero vector and not the number or the scalar zero. So if we write this out in vector form, this is x1 times the vector 1, 1, plus x2 times the vector 3, 5, plus x3 times the vector 11, 4. This is x1, x1, plus 3x2, 5x2, plus 11x3, 4x3. We add the vectors, we get x1 plus 3x2 plus 11x3, x1 plus 5x2 plus 4x3. And we want to find scalars x1, x2, such that x3, such that this is the zero vector. So this is equivalent to the system of homogeneous equations, x1 plus 3x2 plus 11x3 equals 0, and x1 plus 5x2 plus 4x3 equals 0. So we have to solve the system of two equations and three unknowns. So now this is high school algebra, so you can solve these equations any way you like. For example, if you subtract the first equation from the second, you get 2x2 minus 11x3 equals 0. So that says that whenever you solve the system, 2x2 has to equal 11x3, or x2 is 11 halves x3. And from the first equation, for example, x1 is minus 3x2 minus 11x3. That's minus 3. Let's see, x2 is 11 over 2x3 minus 11x3. So if you do your arithmetic, this is minus 55 over 2 x3. So it looks like a solution of the system of homogeneous equations is the vector x1, x2, x3, where x1 is minus 55 over 2 x3, x2 is 11 over 2 x3, and x3 is x3. That's just for any value of x3. So for example, just to get rid of fractions, suppose we let x3 equal 2. Then we get a solution minus 55, 11, 2. And does that work? Let's see, let's check. So this is supposed to be a solution of this system of equations. So let me check. x1 plus 3x2 plus 11x3 is minus 55 plus 3 times 11 plus 11 times 2 is minus 55 plus 55 is 0, so that checks. And x1 plus 5x2 plus 4x3, that's equal to minus 55 plus, oops, good. I thought about that, a mistake. That's always good. Minus 55, 11, 2. Oh, you get minus 55 plus 55 plus 8. And that's not 0. Excellent. So that means I made a mistake. So that's why it's important to check. So let me go back and look at my system of equations. I have x1 plus 3x2 plus 11x3 equals 0. x1 plus 5x2 plus 4x3 equals 0. I subtracted the second from the first. I got 2x2. Ah, perfect. Here's my mistake. So when I subtract, this should be 2x2 minus 7x3 equals 0. So 2x2 is 7 halves x3. And then x1 is minus 3x2 minus 11x3. So that's minus 3 times 7 over 2x3 minus 11x3. So this is minus 21 over 2 minus 22 over 2 is minus 43 over 2. So let me so this should be minus 43. So, oops. So x1, if this is correct, is minus 43 over 2x3. x2 is 7 halves x3. And if I take x equal to 2 just to get a solution that's not a fraction, I get minus 4372. So let me check this again and see if it works. x1 plus 3x2 plus 11x3, that's minus 43 plus 3x2 is 21 plus 11x3 plus 22, that is 0, that checks. And x1 plus 5x2 plus 4x3 is minus 43 plus 5 times 7, which is 35, plus 4 times 2, which is 8, and that's 0, so that checks. So I solved the problem. This is a vector, x1, x2, x3, of scalars, and those scalars are such that this linear combination of vectors is the 0 vector. Okay. Problem 2, I'll just set it up, but it's, again, many problems in linear algebra reduce to problems in linear equations. So in problem 2, we have 3 vectors, 2, 2, 1. So we have 4 vectors, minus 4, minus 3, minus 1, 6, 9, 8, and 10, 21, 9. And we want to find scalars, x1, x2, x3, and x4, such that this linear combination is the 0 vector in R3. If you take this linear combination and write it as a vector, the first coordinate will be 2x1 minus 4x2 plus 6x3 plus 10x4. The second coordinate is 2x1 minus 3x2 plus 9x3 plus 21x4. The third coordinate is x1 minus x2 plus 8x3 plus 9x4. And these all have to be equal to 0 if this linear combination is the 0 vector. So we have to solve 3 equations in 4 unknowns, in 4 variables. So that's a problem in linear equations to do. Okay, that's problem 2. As you have to solve the equations, but that by now you're supposed to be able to do. Problem 3, you have 3 vectors, 5 minus 2, 1, 1 minus 2, 5, and 1, 1 minus 4. And the problem is to write the vector 7 minus 3, 2 as a linear combination of these vectors. So you want to find scalars x1, x2, x3 such that this linear combination of these three vectors gives you this vector. And you have to do that in two different ways. Find two different triples of numbers, x1 and x2, x3, that solve that equation. So the first thing is to find one solution. So if you take this linear combination of vectors, as a vector, this is 5x1 plus x2 plus x3 minus 2x1 minus 2x2 plus x3, x1 plus 5x2 minus 4x3. This linear combination of vectors is this. So we want to find x1, x2, x3 such that this vector equals this vector. And again, that means solving a system, this time of three equations and three unknowns. 5x1 plus x2 plus x3 equals 0. Minus 2x1 minus 2x2 plus x3 equals 0. In the third equation, let me just put it on top, x1 plus 5x2 minus 4x3 equals 0. So again, we have to solve the system of linear equations. How you do it is up to you. For example, let me solve this system of equations this time by writing the augmented matrix of coefficients. 1, 5 minus 4, 5, 1, 1, minus 2, minus 2, 1. So I have this matrix, and I want to put this in reduced row echelon form. So 5, 1, 1, minus 2, minus 2, 1, 1, 5, minus 4. So I can keep the first row fixed. If I add 2 times the first row to the third row, I get 2 minus 2 is 0. 10 minus 2 is 8. Minus 8 plus 1 is minus 7. If I subtract 5 times the first row from the second, I get 5 minus 5 is 0. 1 minus 25 is minus 24. 1 minus 4, sorry, that's minus 5. So it's 1 minus 4 times minus 5 is 20. 1 plus 20 is 21. I get this matrix. I can notice, actually, to save myself some time, the third row is minus 3 times the second row. So if I add 3 times, so here's the third row. I add 3 times the third row to the second row, I get 0, 0, 0. So I have 1, 5 minus 4. Then we interchange the second and third rows. And this row, because I divide it by 8, I get 0, 1, minus 7/8. And then the last step, I have 0, 0, 0, 0, 1, minus 7/8. If I take the first row minus 5 times the second row, I get 1 minus 0, 5 minus 5. Minus 5 times this is 35 over 8. Minus 4 is minus 32 over 8. So if I multiply this by minus 5, I get 35 over 8. Minus 32 over 8. This is correct. This is 3/8. Now, this matrix is in reduced row echelon form. So this system of equations is equivalent to the system x1 plus 3/8 x3 equals 0. x2 minus 7/8 x3 equals 0. So x1 is going to be minus 3/8 of x3. x2 is going to be 7/8 of x3. And x3 is going to be x3. So I can take, so any solution of this system of equations is x1, x2, x3 is a vector of the form x3 times the vector minus 3 over 8, 7 over 8, and 1. And if I want multiple solutions of this system, I take different values of x3. I'll choose the simplest. If I take x3 equal to 8, I get minus 3, 7, 8 as one solution of this vector equation. This is the vector equation I want to solve. And let's just see if it works. So here's my check. So here's my first equation. 5x1 plus x2 plus x3. 5x1 is minus 15 plus 7 plus 8 is 0. That checks. My second equation, minus 2x1 minus 2x2 plus x3. Minus 2x1 is 6. Minus 14 plus 8, that's also 0. That checks. Let's look at the third equation. x1 plus 5x2 minus 4x3. That's equal to minus 3 plus 35 minus 32. That's also 0. So that checks. So any multiple of this solution, minus 3, 7, 8, will work. So you take 2 times that. Minus 6, 14, and 16, for example. Any of those will work. That's problem 3. Let's look at problem 4. We want to find whether certain sets are linearly independent or linearly dependent. So in 4a, we have the vectors 0, 2, and 3, 0. So these are linearly independent if the only solution of the equation x1 times the first vector plus x2 times the second vector equals 0 vector is x1 and x2 equals 0. So we have to solve this vector equation. This vector equation is, so I want 0, 0 to be equal to this. This first vector, that's 0, 2x1 plus 3x2, 0. That's 3x2, 2x1. That's equal to 0, 0 if and only if x1 equals x2 equals 0. So therefore, 0, 2, and 3, 0 are linearly independent. The only, I took these, my 2 vectors, and I take a linear combination of them. When is that equal to 0? So this linear combination, if I work it out, is 3x2, 2x1 equals 0, 0 means 3x2 equals 0, 2x1 equals 0. That can only happen when x1 and x2 are 0. So these vectors are linearly independent. Let's look at D. In D, we have 3 vectors. 1, 2, 2, 3, and 3, 4. And we want to know what linear combinations of these vectors give you the 0 vector. So what is this? This is x1 times the vector 1, 2 is x1, 2x1. x2 times 2, 3 is 2x2, 3x2. x3 times 3, 4 is 3x3. Sorry, 3, this is a 1. So this is 3x3, 4x3. So when I add them up, I get x1 plus 2x2 plus 3x3, 2x1 plus 3x2 plus 4x3. If that's the 0 vector, then x1 plus 2x2 plus 3x3 has to equal 0, and 2x1 plus 3x2 plus 4x3 has to equal 0. So again, I have to find the solution space of this system of homogeneous equations. And again, how I do it is, how you do it is up to you. I write the matrix of coefficients, and I put this in reduced row echelon form. If I take the second row minus 2 times the first row, I get 2 minus 2, 3 minus 4, 4 minus 6. And if I multiply the second row by minus 1, I have plus signs. But then if I add 2 times this row to this row, or subtract 2 times this row from this row, it's the same thing. The first row plus 2 times this row is 1 plus 0, 2 minus 2, 3 minus 4. I get this matrix, I think. So this system of equations is equivalent to the system x1 minus x3 equals 0, x2 plus 2x3 equals 0, which means x1 has to equal x3, x2 has to equal minus 2x3. So if I take any vector x1, x2, x3, where x1 is x3, x2 is minus 2x3, and x3 is x3, this means any scalar multiple of 1 minus 2, 1. This is a non-zero vector that solves the system of equations. Let's just check. If I take 1 times the vector 1, 2, minus 2 times the vector 2, 3, plus 1 times the vector 3, 4, this is 1, 2, minus 4, 6, plus 3, 4, and I add them up, and I do get 0, 0. It checks. So my system of vectors, these 3 vectors, are linearly dependent, not independent, because there's a non-zero set of scalars, x1, x2, x3, that makes this linear combination equal to 0. Problem 4 is similar, except working in R3 instead of R2. So let me look at problem 5 is vectors in R3 instead of R2, but the method is exactly the same. Let's look at number 6. We want to prove the set of vectors v1, v2 is linearly independent if and only if the set of vectors v1 plus v2 and v1 minus v2 is linearly independent. So we have to prove 2 different statements. If this set is independent, so is this. That's the first statement. The second statement is if this set is independent, then so is this. So step 1, suppose v1, v2 is an independent set of vectors. Suppose we have the 0 vector can be written as x1 times v1 plus v2 plus x2 times v1 minus v2. So suppose a linear combination of these 2 vectors is 0. That's what this means. If we rewrite this, I have v1, I have x1 plus x2 v1, and I have x1 minus x2 v2. Just expand this and rearrange, and this is what you get. But v1 and v2 are independent. So this means the scalars x1 plus x2 and x1 minus x2 have to both be equal to 0. And if you add these equations, you get 2x1 equals 0. So x1 is 0, and if x1 is 0, x2 equals 0. So that's the proof in one direction. If this set v1, v2 is independent, so is this set. And step 2 is to work in the opposite direction. Suppose V1 and V2 are independent, and take a linear combination, say x1 V1 plus V2, suppose the second set is independent, that's the second one. So suppose V1 plus V2 and V1 minus V2 is an independent set of vectors. And consider 0 as a linear combination of V1, x1 V1 plus x2 V2. So I must show x1 and x2 are equal to 0. So I would like to be able to express this as some linear combination of V1 plus V2 and V1 minus V2. So suppose I can find scalars, let me call them y1 and y2. So I would like to write x1 v1 plus x2 v2 in the form y1 v1 plus v2 and y2 v1 minus v2. If I can do that, then what do I have over here? This is y1 plus y2 v1 plus y1 minus y2 v2. So I would like to find y1, y2 such that y1 plus y2 equals x1 and y1 minus y2 equals x2. And so I want to solve these equations for x1 and for y1 and y2. If I add, I would get that y1, 2y1 is x1 plus x2. So y1 is x1 plus x2 over 2. And if I subtract, I would get y2 is x1 minus x2 over 2. So I have a vector equation. By a miracle, I was able to find it. If 0 is x1 v1 plus x2 v2, this is exactly the same as x1 plus x2 over 2, v1 plus v2, and x1 minus x2 over 2, v1 minus v2. So my linear combination of v1 and v2 can be rewritten in this form. But we're told that the two vectors v1 plus v2 and v1 minus v2 are linearly independent. So that means x1 plus x2 over 2 equals 0, and x1 minus x2 over 2 equals 0. And if you add and subtract these equations, you get x1 equals x2 equals 0. So that says that if the vectors v1 plus v2 and v1 minus v2 are independent, then so are v1 and v2. That's the proof of problem 6. Now, if you have not taken a course in mathematics before where you had to learn, be able to follow proofs, understand proofs, and write out your own proofs, the more time you spend studying a problem like this and its solution, the better prepared you are in this and other courses. Proofs are important. Okay. Let's look at problem 13 in this set. So in 13, we have W1 is the subspace of R2 generated by the vector E1 equal to 1, 0. And W2 is the subspace of R2 generated by the vector E2 equals 0, 1. We want to compute W1 intersect W2. and also show that W1 union W2 is not a subspace. So again, we go back to high school algebra. The vector E1, it's just this point in the plane, 1, 0. So the subspace W1 is just all scalar multiples of this. It's the x-axis. This is W1. This line through the origin, the horizontal line through the origin. The vector 1, 0, 1 is that vector. And if you look at all scalar multiples of that, you get this second line through the origin, the y-axis. So W1 is the green line, the x-axis. W2 is the orange line, the y-axis. The only point of intersection is the origin, or coordinates 0, 0. That's what W1 intersect W2 is. W1 union W2 is just the union of these two lines, the green line plus the red line. And this is not a subspace because, for example, it is not closed under vector addition. I have the vector E1 is in W1 union W2. The vector E2 is in W1 union W2. But if I take E1 plus E2, I add these two vectors, that's the vector with coordinates 1, 0. That's right over here. That's E1 plus E2. Coordinates 1, 1. That's not on the green line. It's not on the orange line. So this is not in W1 union W2. So this union is not a subspace. It is not closed under vector addition. Let me go on to section 4.3. Page 219. Problem 1 is to find a basis for the subspace of R2 generated by certain sets of vectors. So in 1A, we have a set 1, 0 consisting of the vectors 1, 0 and 0, 2. In the plane, this is the vector 1, 0. This is the vector 0, 2. That's 1, 0. Here, that's 0, 2. If I look at the set of all linear combinations, x1 times 1, 0 plus x2 times 0, 2 for all x1 and x2, that's all vectors of the form x1, 2x2 for any choice of x1 and x2, any scalars. But this is all vectors. Like, for example, take the vector 7 minus 3. That's equal to 7 and 2 . minus 3/2 times 2. Or 2 times minus 3/2. That's a better way to. So this is equal to 7 and 2 times minus 3/2. If I choose x2 to be minus 3/2, I get minus 3. If I choose x1 to be 7, I get 7. So this set is all of R2. So these two vectors generate R2, and it's also the case that 1, 0, and 0, 2 are linearly independent. So the set 1, 0, 0, 2 is a basis for R2. A basis for a vector space is a linearly independent set of vectors that generates the space. These two vectors are linearly independent and they generate R2. So this is the basis. Let's look at 1b. S2 is the set of vectors 1, 1, and 1, minus 1. Again, if you look at this in the plane, there is 1, 1. Here is 1, minus 1. And what is the subspace these generate? Well, I claim if I take any vector AB in R2, I can write AB as some linear combination of 1, 1 and 1, minus 1. That is, I can write AB in the form x1 plus x2 and x1 minus x2. I can do that if I can solve the equations x1 plus x2 equals A and x1 minus x2 equals B, which if I add gives me 2x1 is A plus B, so x1 is A plus B over 2. If I subtract, I get 2x2 is A minus B, so x2 is A minus B over 2. So every vector AB in R2 can be written as a linear combination of these two vectors. It's A plus B over 2 times the vector 1, 1 plus A minus B over 2 times the vector 1, minus 1. So the subspace generated by S2 is all of R2. And I also claim these two vectors are linearly independent because if x1, 1, 1 plus x2, 1, minus 1 is the 0 vector, that means that x1 plus x2 is 0 if you look at the first coordinates. x1 minus x2 is 0 if you look at the second coordinates. And the only solution of these equations is x1 equals x2 equals 0. So S2 is linearly independent, the linearly independent set of vectors. So S2 is a basis for R2. These two vectors have the property that every vector in R2 is a linear combination of them, and they are linearly independent. Let's look at part B of this problem. So S4 is the set of vectors 1, 1, 1, minus 1, and minus 1, 1 contained in R2. So we just saw in part B that just these two vectors generate R2. And there's no subspace of R2 bigger than R2. So S4 certainly generates R2. Every vector in R2 generates, it's a linear combination of these vectors. Actually, I should have stated this problem slightly better. I wanted to find a subset of S4, which is a basis for R2. These vectors are linearly dependent. Suppose I want to write 0, 0 as a linear combination of 1, 1, 1 minus 1, and minus 1, 1. So this is x1 plus x2 minus x3, x1 minus x2 plus x3. I want to solve the equations x1 plus x2 minus x3 equals 0, x1 minus x2 plus x3 equals 0. What are the solutions of these equations? If I add the equations, of course, I get x1 equals 0, but then it also says x2 equals x3. So I could take any vector of the form 0, x2, x2, or x2 times 0, 1, 1, and that will give me a linear combination of these vectors equal to 0. For example, this is just the most trivial example. 0 times 1, 1, plus 1 times 1 minus 1, plus 1 times minus 1, 1 is 0. So here is a linear combination of these three vectors, but not all the coefficients are 0. Two of these are equal to 1. So these vectors are linearly dependent. So S4 is not a basis for R2. S4 is not a basis for R2. It generates R2. And if I take, for example, just the first two vectors, that is a basis for R2. So that's that. Let's go to problem 3 in section 1.2. So we take a B, which is a basis, we're told, for R3, where B1 is the vector 1, 1, 0, B2 is the vector 1, 0, 1, B3 is the vector 0, 1, 1. And I want to compute the coordinate vector for 3, 4, 5 with respect to this basis. What this means is I want to take the vector 3, 4, 5 and write it as a linear combination of V1, V2, and V3. So x1, 1, 1, 0 plus x2, 1, 0, 1 plus x3, 0, 1, 1. This is the vector x1 plus x2. This is the vector x1. This is the coordinate x1 plus x3. And the third coordinate is x2 plus x3. So I need to find scalars x1, x2, x3 such that x1 plus x2 equals 3, x1 plus x3 equals 4, x2 plus x3 equals 5. I need to solve this system of equations. So again, you have many choices to do it. I'm going to write down the augmented matrix. The matrix of coefficients is 1, 1, 0, 1, 0, 1, 0, 1, 1. And I augment it by the right-hand column, 3, 4, 5. So I want to put this matrix in reduced row echelon form. I have 1, 1, 0, 3, 0, 1, 1, 5. If I take the second row minus the first row, I get 1 minus 1 is 0, 0 minus 1, 1 minus 0, 4 minus 3. If I add the third row to the second row, I get 0, 0, 2, 6. And this is my third row. Let me interchange the second and the third rows. And let me take the first row minus this row. I get 1 minus 0, 1 minus 1, 0 minus 1, 3 minus 5. Looks like that's what I get. So this is 0, 0, minus 1, minus 2, 0, 1, 1, 5. And if I multiply the third row by a third, I get 0, 0, 1, 3. And then, so I have 0, 0, 1, 3. If I add the third row to the first row, which should be a 1 over here. 1, 0, 3. 1 minus 0, 1. That's 1. If I add the third row to the first row, I get 1, 0, 0, 1. And here I have my second row. If I subtract my third row from the second row, I get 0, 1, 0, 2. I have this. So this is equivalent to the system x1 equals 1, x2 equals 2, x3 equals 3. So that's my linear combination. And you can check if you put in x1, x2, x3, that's what you get. So the coordinate vector of the vector 3, 4, 5 in R3 with respect to the basis B, which is this basis I started with. The basis B that I started with is, if I take this vector B, 3, 4, 5, the coordinates with respect to the basis B are 1, 2, 3. This does not mean that the vector V is the vector 1, 2, 3 in three-dimensional space. It means with respect to the spaces B, the vector B is 1 times the first basis vector plus 2 times the second basis vector plus 3 times the third basis vector. This is a somewhat subtle point that you need to spend some time thinking about and understanding. And that is essentially homework 2. So we just covered homeworks 1 and 2 in chapter 4.